Hello and welcome back. Today we're going to learn about 4.2 Bernoulli binomial probabilities. Sometimes these are going to be referred to as Bernoulli problems. Other times I'm going to refer to them as binomial probabilities. In this video I'm also going to be pausing every once in a while and posing a question to you, so when it gets to that point make sure you answer the question correctly before moving on. So let's get to it. A binomial distribution, otherwise known as Bernoulli, needs to have certain characteristics in order to be able to do this method. Okay, it first needs to be repeated situations called trials. Okay, it's not just once; it's just going to be a bunch of trials. There's also going to be a maximum of 2 possible outcomes, always 2 actually: success and failure. Something happens or it doesn't happen. Okay, those are the only 2 possibilities. The trials are going to be independent from each other. I mean, they're going to all happen at separate times. And each trial will have the same probability of success. This is a very important feature of Bernoulli's or binomial problems, is that it has a fixed probability associated with it. Okay, anything that's a fixed probability. So the chances that something's going to happen, that you're going to have success, is going to be the same for every trial. Okay, and then there's going to be a fixed number of trials. Now, when I say success, by the way, success usually means a good thing, right? So you're successful. But what that really means in this situation is what you want to have happen. Okay, so if I say the probability that you miss a certain number of follow shots, and I'm looking for what's the probability that you're going to miss 4 of the next 5 foul shots. Missing the foul shots is considered a failure. However, in these cases it's considered a success. So success just means what you're trying to look for. Okay. For the Bernoulli problems, you're going to set up your problems like this. You're going to start with NRPQ. Okay. N is going to be the number of trials. R is going to be the number of successes. P and Q are going to be your probabilities. P is the probability of success. And as you can guess, Q is going to be the probability of failure. One thing to note about these Bernoullis is that the probability of success and failure will always add up to 1, because 1 constitutes 100% of the chances that's going to happen. So if P is 0.7, Q would be 0.3. If P is 2/3, Q is 1/3. So they can be represented as decimals or as fractions. Okay, depending on the problem will depend upon which one's more appropriate to use. Now the Bernoulli formula is going to be found by adding up a bunch of terms. So it's going to be the summation of all the NCRs, P to the R, Q to the N minus R. Note a very important thing here. Okay, for these Bernoulli probabilities, this R right here is going to be always the exponent on the P. Okay, and then this right here, the N minus R, is always going to be what adds up with R to make N. You can think about it in that way. So let's look at some problems. Pause the video now, write down anything you need to. Okay, let's look at the first problem. Okay, 4 patients are being treated for an illness. The probability that the illness will be cured is 0.7. So cured, the probability for cured is 0.7. That means the probability that they're not cured is going to be 0.3. So the first problem, let's set up our NRPQ. Notice in the problem we have 4 patients are being treated for illness, so the number of people we have is always going to be 4 in this case. For letter A, it says, what is the probability that only 3 patients will be cured? So we're looking at being cured. That's going to be our success. And only 3 patients is going to be our number of successes. We want to have 3 cured. That's going to be my R value. Being cured is 0.7, so P is 0.7, which means that Q must be 0.3. So the probability is going to be 4C3 0.7 raised to the third times 0.3 raised to the first. Notice this 3 right here is going to be the same as that 3 up there. And to make 4, the next one's going to have a 1. Okay. And to calculate this, 4C3, as we learned in previous lessons, is equivalent to 4C1, which is equivalent to 4. 0.7 raised to the third, type that in your calculator, you get 0.343. And 0.3 to the first is 0.3. And when you multiply that all out, you get an answer of 0.4116. That is the probability that only 3 patients will be cured. Now let's look at an example we have not just 3 but more. Okay. So what is the probability that 2 or 3 patients will be cured? Okay, so we're still looking at being cured. We're not looking at not being cured. So our success is going to be, our p-value is going to be 0.7 still. So let's set up NRPQ. Our N is still 4. Now our R is going to be 2 and it's going to be 3, and this is going to be indicating that we're going to have 2 terms we're adding together. Our probability of success, our P value is 0.7 and our failure rate is 0.3. So we're going to set up the probability by saying 4C2 0.7 to the second 0.3 to the second. Notice these 2 things add up to the 4. But we're going to add in as well for the 3 patients. So we're going to have 4C3 0.7 to the third times 0.3 to the first. So let's look at this first one. So 4C2, okay, that's going to be 4 times 3 divided by 2 times 1. So it's going to be 6. 0.7 squared is 0.49. 0.03 squared is 0.09. And notice up from part A, we already solved for the probability only 3 patients, so we can just use that value. There's no need to recalculate it if in an earlier part of the problem we calculated that probability. There's no need to calculate what that's going to be again. But 6 times 0.49 times 0.09 is going to be 0.2646. We're going to add that to the 0.4116, give me a total probability of 0.6762. Okay, pause the video now and write down anything you need to. Alright, moving on. Alright, here's another example of a Bernoulli situation. Suppose a multiple choice quiz has 10 questions, each with 5 choices. If a student answers by random guessing, what is the probability that at least 3 questions are answered incorrectly? Okay, so let's set up our NRPQ. NRPQ. Now we have a multiple choice quiz that has 10 questions, so our N is going to be 10. There's 5 choices, so the chance that you're going to get a correct answer is going to be 1 out of 5, and an incorrect answer is going to be 4 out of 5. And we're looking at for probability of incorrectly answering questions, so I'm going to use my p-value as the 4 out of the 5, and then therefore my q is going to be 1 out of the 5. Okay. You could also write that as a decimal if you choose to, 0.8 and 0.2. Okay. Now it says we want to know the probability with random guessing that at least 3 questions are answered incorrectly. So we're looking at 3, 4, 5, 6, 7, 8, 9, and 10. Whoa, that's a lot of things to add up together. Alright, so in this situation, what you can do is actually look at the complement of this. Complement means everything that's not part of the R. Okay, and we're just going to take that away from 1 because the probability of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 added up together are all possibilities. That should always add up to 1. And it will. So we want to look at just for the R values of 0, 1, 2. So if we use that, find that probability, and subtract that from 1, that'll give us the probability of 3, 4, 5, 6, 7, 8, 9, 10 without having to add up all those 8 terms. Okay, so let's plug into the Bernoulli formula. So we're going to have a long, still fairly long thing here, but we're going to do 1 minus, and then we're going to put in 10C0. I'm going to use decimals, 0.8 to the 0, 0.2 to the first, to the 10th, sorry. These two numbers have to add up to, that's a 0. There you go, that's a 0. That's a better 0. Alright, so those two numbers have to add up to that n value. Okay, and this first exponent is always going to be the same as the r value there. We're going to add it to 10C1, 0.8 to the first, 0.2 to the 9th, plus 10C2, 0.8 to the second, 0.2 to the 8th. Whew, I just barely made it there, didn't I? Okay, if you need to go on the second line, that's fine. Just make sure you close the print at the end. Okay. Now, let's calculate each of these 3 terms, but keep visual to make sure you keep that parenthesis there, the 1 minus parenthesis, or in this case a bracket. This is 10C0 is going to be just 1. 0.8 to 0 is going to be 1. Now if you type in 0.2 to the 10, do that for a second. Notice your calculator probably says this. It probably says 1.024 e negative 7. Okay. What that is really saying is that your calculator cannot type in all the digits in because the numbers are going to be too far away from the decimal point. Okay, so the calculator will give you this answer instead. But what that's really saying is you're taking the decimal point and you're moving it, since it's negative 7, to the left 7 spaces. Or in other words, this number before the decimal is going to be in the 7th spot after the decimal. So this is going to be equivalent to 0.000001027. That's what that is really representing. Okay, there might be more digits than that because your calculator can only round to a certain value, but that's essentially what it is. Your calculator can't show all that. Okay. So that means you have 1 times 1 times 0.000001027. 24. Ooh, okay. And then we're going to add that to the next probability, which is going to be 10. Now, if you type that in your calculator, 10 times 0.8 to the first times 0.02 to the 9th, you will get 0.000004096. Very small probabilities, isn't it? Okay. And then 10C2, so that's going to be 10 times 9 over 2 times 1 using the shortcut, so that's 5 times 9, which is 45. So 45 times 0.8 squared times 0.02 to the 8th, 0.000073728. So once you plug it into the formula up here, okay, this whole bit up here, make sure that you at least write down for the next step what each of the 3 terms are going to be before you add them up. Don't just add them all up at once. Okay, write down each term. Now we can add all those up in our calculators, and doing so we get 0.000077924. So subtract that from 1, you get 0.99992200736. And it's probably more decimal places than that, but that's all our calculator can say, so ... Which means, and probabilities, by the way, are going to be usually rounded to 4 decimal places, so the probability that we have at least 3 questions answered incorrectly is 0.9999. Okay. Phew, that was a lot. Pause the video, write down anything you need to before moving on. Okay. Now let's look at this last question. Okay, so this question I'm going to focus on when you use fractions and how that might be used instead of decimals, because sometimes fractions are a little bit better. So let's look at this problem. A fair coin is tossed 5 times. You want to find the probability first that there are no more than 2 tails. So let's first set up our NRPQ. Ooh, those are pretty big equal signs. Pen's not working very well right now. Okay, so what is my n? My n is 5, because it's tossed 5 times. You want to know the probability of no more than 2 tails. So that means you're going to be 0, 1, or 2 tails. You want a tail, and if it's a fair coin, that means it's going to be equal probability of heads or tails, so it's going to be 1 out of 2. Therefore, the probability of failure, which is probability of getting a heads, is 1/2. So we have 3 things for R. We're going to add 3 different summations. So plugging into the Bernoulli formula, we get 5C0, and I'm going to use fractions just to illustrate what happens with the fractions. 1/2 to the 0, 1/2 to the 5th, and 5C1, 1/2 to the 1st, 1/2 to the 4th, plus 5C2, 1/2 to the 2nd, 1/2 to the 3rd. Okay. 5C0 is 5, 1/2 to the 0th, anything to the 0 is always 1, and 1/2 to the 5th is going to be 1/32. Notice essentially what you did there is just 1 to the 5th in the top, 2 to the 5th in the bottom, 2 to the 5th is 32. Which, if you type that in your calculator, 1 divided by 2 raised up to the 5th power, you get 0.03125, which is a nice decimal, but 1/32 is actually taking up less space. So maybe this is a good example of where fractions are easier to deal with. Okay, the next term, 5C1 is going to be 5. 1/2 to the 1st is 1/2. 1/2 to the 4th is going to be 1/16. Okay, 5C2. That's 5 times 4 divided by 2 times 1, so it's going to be 5 times 2, which is 10. Times 1/4 times 1/8. Now let's add up those fractions. Now notice in this case, no matter what you're going to get for the denominator, it's going to be the same thing. Because you have 2 to the 0th times 2 to the 5th, 2 to the 1st times 2 to the 4th, but you're always going to get 2 to the 5th in that denominator. So your denominators are going to be always the same. That makes these problems also a little bit easier because you don't have to worry about common denominators. So you just have to multiply the numerators. 5 times 1 times 1 is 5. 5 times 1 times 1 is 5. 5 times 1 times 1 is 5. Oh, sorry, 10 times 1 times 1 is 10. Whew. Hopefully you caught me there. 5, and then since they're all the same denominators, you just add the tops. 5 plus 5 plus 5 is 5 plus 5 plus 10 is 20 over. Ooh, wait a second. Hopefully some of you realize that this should not have been a 5. That should have been a 1. Haha. Alright, that was a little better. Okay. So 1 plus 5 plus 10 is 16 over 32, which is 1/2. So the probability of no more than 2 tails is 1/2. Or if you really want to, write as a decimal, 0.5. My apologies for that mistake. I'm already 20 minutes in and I don't feel like recording this video. Okay. Alright, one more problem. Find the probability of odd numbers of heads. So NRPQ. Still got 5 trials because we have 5 times that we will be tossing the coin. We want an odd number of heads. So the odd number of heads is going to be 1, won't be 2, it'll be 3, won't be 4, it'll be 5, won't be 6, because you're not going to have 2, 4, 6. Those are even number of heads. Probability of success is the probability of getting a heads, which is 1/2. So the probability of failure must be 1/2. Okay, so let's plug that into the Bernoulli. 5C1, 1/2 to the first, 1/2 to the fourth, plus 5C3, 1/2 to the third, times 1/2 to the second, plus 5C5, 1/2 to the fifth, times 1/2 to the 0th. 5C5, I'm not going to make this mistake this time. This one is 5. Okay, times 1/2 times 1/16. 5C3, that is 5 times 4 times 3 divided by 3 times 2 times 1. 3's cancel. That's going to be 10 times 1/8 times 1/4. 5C5 is the same thing as 5C0, so that's going to be 1 times 1/32 times 1. So we have 5 over 32, because 5 times 1 times 1 is 5, plus 10 over 32, plus 1 over 32. And that all adds up into 16 over 32, and coincidentally, we get the same answer as part A. So 1/2 or 0.5. Now, of course, that won't always happen in these fair coin problems. If I said the probability of 2 heads, then that would obviously not be 1/2. That would be a little bit less. Okay, pause the video now, write down anything you need to before moving on. Okay, so let's just sum up this lesson a little bit. So we looked at Bernoulli today, sometimes called binomial probabilities. And key things to keep in mind with Bernoulli and the binomial probabilities is that you need to have a fixed number of trials. You need to have a fixed probability. Okay, that's an L there, I promise you. And also you need to have success and failure. Or in other words, 2 outcomes. Only 2 outcomes. Yeah, my writing's getting sloppy. Only 2 outcomes. There you go. Alright, so that's Bernoulli. So hopefully you enjoyed this video, and look forward to the next one. Thank you.